Swayam Prabha. Digital India. Educated India.
So, so we start with two curves. Okay, so you start with gamma 1 comma gamma 2, both unit speed parameterized. So by arc length, by increasing arc length, S in open interval AB, okay, and such that both the curves have the same curvature and the same torsion. So k of k gamma 1 of S is equal to k gamma 2 of S, and so the curvatures are the same, and the torsion gamma 1 S is equal to the torsion gamma 2 of S. Okay, so you start with this. Then the fact is that there is a rigid motion that moves gamma 1 to gamma 2. Now how did we do that? So what you do is you have this, so this is gamma 1 of S, okay, and you fix a point basically so before that, okay, what I want you to first notice is that you see the curvature and the torsion are the two terms that occur in the Frenet-Serret differential equation. Okay, so basically what this means, the fact that the curvatures and the torsions are the same means that already the Frenet-Serret frame of gamma 1 and the Frenet-Serret frame of gamma 2, they satisfy the same differential equation. Okay, so you see the Frenet-Serret frame of gamma 1 of S satisfies so the T cap, N cap, and the last one is B cap, and here also it should be B. So here left side is B cap dot and right side is B cap, and of course here dot is D by ds. Okay. So you see the moment you take this curve gamma 1, there is the there is a curvature function, there is a torsion function, and then here is a Frenet-Serret relation. Similarly, if you take gamma 2, also you have a similar Frenet-Serret differential equation. The fact that the curvatures and the torsions are the same mean that this part, this coefficient matrix, okay, this Q symmetric matrix, Frenet-Serret matrix if you want to call it, that is the same for both the curves. That means that the Frenet-Serret frame of the first curve as well as the Frenet-Serret frame of the second curve, they are both solutions to the same differential equation. So the point I want to say, so let me just put I'll just modify this to put it as I here and say that so let me put it like this. I'll just replace the 1 by I. Okay, so I'll put gamma I. So I is equal to 1 comma 2. So if I put it for I, then the matrix here I can, this k gamma 1 is the same as k gamma 2. Okay, minus k gamma 1 is the same as minus k gamma 2. Okay, tau gamma 1 is the same as tau gamma 2, and minus tau gamma 1 is the same as minus tau gamma 2. Okay, so that is basically what you have is the Frenet-Serret frames of gamma I of S, okay, satisfy the same the same differential equation. Okay, in fact, what kind of differential equation it is? You see, it's a first order ordinary linear simultaneous homogeneous differential equation. So So let me write that this is first order linear homogeneous simultaneous ODE. Okay, and basically what you are trying to say is, see, once you have this, so this is the conclusion from the fact that both the curves have the same curvature and torsion functions. Okay, from this you want to say that one curve can be moved to the other by rigid motion. Okay, now so the question is that, you know, that means there is a rigid motion. If you move the first curve by that rigid motion, it should superimpose on the second curve. Okay, and if it superimposes on the second curve, basically what it means is that, you know, if two curves are the same, then their Frenet-Serret frames must be the same. Okay, and basically it means therefore that these two Frenet-Serret frames, which are satisfying the same differential equation, which are two solutions of that differential equation, they have to be the same solution. Okay, now when will two solutions of a differential equation be the same? They will be the same if and only if they satisfy you know, the same set of initial conditions. Okay, therefore the moral of the story is, if you want to use the idea of uniqueness of solutions, particular solutions of differential equations, what you should attempt to do is that you try to make both the Frenet-Serret frames to satisfy the same initial condition. Okay, but what is the initial condition? It has to be that the Frenet-Serret frames should be the same at a given point. Okay, but you see, if the Frenet-Serret frames have to be same at a given point, first of all, that point should be, you know, common to both the curves. All right, so the first thing that you have to do is that make sure that both the curves intersect. So that is the reason what you do is that you take this point, you for a particular parameter value s naught in AB, what you do is that you have gamma 1 s naught, and then there is, here you have this gamma 2 of s, and here you have gamma 2 of s naught. Okay, so first of all you make the two curves to intersect at one point. So what you do is that you first apply a translation. You apply a translation that will take this to this. So that is the translation TV naught. Okay, and that translation is just, you know, it is just translation by this vector joining gamma 1 s naught to gamma 2 s naught. So this is just, you know, T of translation by gamma 2 s naught minus gamma 1 s naught. You do this translation. After you do this translation, what happens is that, you know, the first curve, now what you have achieved is, you know, the first curve is now translated like this. It goes here. So you get T V naught circle gamma 1 of s. Okay, you get this curve you get. And this curve, now what has happened is that this curve is now, you know, intersecting gamma 2 at that point, at the same point, which is gamma 2 s naught. Okay, now, but you see, if I want again go back, if you want two solutions of a differential equation to be the same, you should have the same initial conditions. So what, and mind you, what does the differential equation solve for? The differential equation solves for only the Frenet-Serret frame, not for the curve. Okay, so and how do you get the curve from the Frenet-Serret frame? That is very, very easy, because you see, once you get T cap, okay, once you get T cap is just going to be you know, gamma dot. So always the rule is that, you know, if you get T cap, you integrate it, you get gamma dot. Okay, so even though the Frenet-Serret differential equation is solving for T cap, N cap, B cap, integrating T cap should in principle give you back your curve. Okay, so it is connected with the curve. The only thing is, with respect to the curve, the Frenet-Serret differential equation is third order. Okay, because it involves K and it which is second order derivative and which involves the second order derivative, and the torsion which involves the third order derivative. Okay, whereas in the Frenet-Serret frame, it's only first order. That's the point. Okay, so you see, therefore, what do you have to do? Remember, you want both the Frenet-Serret frames to have the same initial conditions. First of all, that means that, you know, they should pass to the same point. Okay, that has been managed for this translate T V naught circle gamma 1 and gamma 2. They both pass to the same point. then you need to set the initial condition, namely the Frenet-Serret frames of these two, they have to become the same, but they will not be. What will happen is that the Frenet-Serret frame of TV0 circle gamma 1 and the Frenet-Serret frame of gamma 1 will be the same, okay, because when you make a translation, the Frenet-Serret frame is not going to change, but the Frenet-Serret frame of gamma 2 at S0, that may be different. So what happens is that at the point gamma 2 S0 where these two curves intersect, you have two Frenet-Serret frames and both are orthonormal right-handed frames, and there is a rotation that takes one to the other. So you apply that rotation. So what you do is that you see here you do this extra thing to make the initial conditions the same. So what you will do is that you will simply do the following thing. So let me write it here. So what you do is now you apply a rotation G1. Okay. Now G1 is a rotation. What does G1 do? G1 takes the Frenet-Serret frame of TV0 circle gamma 1 to that of gamma 2 at S0. You apply this rotation. Okay. So what will happen is after you apply this rotation, this G1 circle TV0 circle gamma 1, okay, I think that is the notation I have used. Yes, that is the notation I have used earlier. So so you see this GV1 circle TV0 circle gamma 1, that is this TV0 circle gamma 1 rotated by this G1, and G1, mind you, is a rotation about gamma 2 S0, not rotation about the origin. Okay, you can write it in terms of rotation about the origin, that I have already done. Okay, it's easy to do that. But the point is now you get a new curve. So the new curve that I am getting, so let me again draw it. I think I can probably I can use red. Okay, so what happens is that I get another curve like this. This red curve is G1 circle TV0 circle gamma 1 of S. This is the new curve. All right, and what have we managed to do? What we have managed to do is that now these two curves, this gamma 2 and GV1 circle TV0 circle gamma 1, they both pass through the same point gamma 2 S0, and both of them have the same Frenet-Serret frame at gamma 2 S0. Mind you, this G1 is a oriented rotation because it's taking an oriented right-handed frame to another oriented right-handed frame, and if any rotation that takes a right-handed frame to a right-handed frame is by definition oriented. Okay. Therefore, moral of the story is that, see, we have achieved this. What has happened is that this gamma 2 and this other curve, which is G1 circle TV0 circle gamma 1, they both pass through the same point gamma 2 S0, and at that point they both have the same Frenet-Serret frame. Okay, but now here comes the important thing. You see, whenever you apply rigid motion, the curvature and torsion functions will never change. Therefore, this gamma 2 as well as this new curve, which is G1 circle TV0 circle gamma 1, they still have the same Frenet-Serret matrix. They are still both solutions of the same Frenet-Serret differential equation, but now they are both solutions with the same initial condition. Therefore, by the theory of uniqueness of solutions of differential equations, they have to be the same. Therefore, you will get for all S. Okay. So in fact, what will happen is that this red curve that I have drawn will actually superimpose on the purple curve, which is the gamma 2. Okay. So that is how the uniqueness of the theory of differential equations is used. Okay, and you have also found the rigid motion. The rigid motion is basically this G1 circle TV0. It's a translation followed by a rotation. Okay, so you have found a rigid motion that moves this curve to the other curve. Okay, now what I want to say is that what is so let me write this down. Since GV, so since G1 circle, so let me write this. Since G1 circle TV0 circle gamma 1 and gamma 2 have the same initial conditions at gamma 2 of S naught, they and they satisfy, and they are both solutions of the same Frenet-Serret ODE, okay, they have to be the same. They have to be the same. That is, you get G1 circle TV naught circle gamma 1 is equal to gamma 2, and that can be written as M circle gamma 1 is equal to gamma 2. Okay, and where this M is this G1 circle TV naught is a rigid motion. Okay, so this is what we have done. All right. Now, what I want to say is that even without using the uniqueness of solutions of differential equations, okay, you can directly deduce this, because to deduce that these two are equal, you can do it even using the Frenet-Serret relations themselves. The Frenet-Serret relations are very, very powerful. Okay, so how will you directly do that? So you see, if you look at it, but this equality can be seen by using the Frenet-Serret differential equations directly. Okay, so what you do is you put gamma 3 to be this new curve G1 circle TV naught circle gamma 1. Okay, and we want to show that gamma 3 so I have to say something here. So again, I have again and again, I have skipped something. So which so let me. So the idea is, okay. So let me tell you what I have skipped. Okay, whenever I am thinking of the curve, but I am looking at the Frenet-Serret differential equations, I am only looking at the Frenet-Serret frame, not the curve itself. So in principle, this line I have to, what I meant was that you see these two, it's not these two curves, but it's rather their Frenet-Serret frames that have the same initial conditions. Okay, and you have to remember that and when I say they are both solutions of the same Frenet-Serret ODE, it means that you solve for the Frenet-Serret frame and integrate the first vector, which is a tangent vector, to get gamma. So if I want to say it carefully, what I should say is, since the Frenet-Serret frame of this and the Frenet-Serret frame of gamma 2 have the same initial conditions at gamma 2 S naught, they are both solutions of the same Frenet-Serret ODE, therefore they have to be the same. Okay, and what this will give you, this will only give you, so I will put these things in brackets, so they have to be the same, means what? The Frenet-Serret frames will be the same. So what you will get, you will get T cap, B cap, N cap of this G1 circle TV naught circle gamma 1 is the same as the T cap, B cap, N cap for gamma 2. This is what you will get. Okay, but this will give you T cap of G1 circle TV naught circle gamma 1 is equal to T cap of gamma 2. You have to integrate that from S naught to S to get G1 circle TV naught circle gamma 1 equal to gamma 2. Okay, so I'm sorry I meant that, but I didn't say it. So let me write it here. For I already said this, but let me say this. So so what happens is that T cap of G1 circle TV naught circle gamma 1 is the same as T cap of gamma 2. Okay, But you see, what is t cap? It is d of the curve by ds. So this is actually d by ds of g1 circle tv naught circle gamma 1, and the thing on the other side is d by ds of gamma 2. Okay, now what you do is you integrate from s0 to s. So what you will get is g1 circle tv naught circle gamma 1 at s minus g1 circle tv naught circle gamma 2 uh, at s0. This is integral from s0 to s d by ds of g1 circle tv naught circle gamma 1. That is integral from s0 to s of d by ds of gamma 2, and that will give you gamma 2s minus gamma 2 of s0. Okay, and notice that this guy here is the same as this guy. Therefore, g1 circle tv naught circle gamma 1 s is gamma 2 s, and that is exactly what I have directly written here. Okay, so this is a common thing that you will do. You will solve for the the Frenet-Serret frame and integrate the tangent vector, which is the first member of the frame, and you will get the curve. Okay, so there is something, when I directly wrote this the first time, I skipped that, but it is understood. But anyway, I am just reminding you of that. Okay, so that's something I missed, I just remembered. So let me keep that aside and go back to whatever I was doing. So you see, I was now trying to say that this equality of these two curves here, okay, can be seen directly from the Frenet-Serret differential equation. And how is that? It is enough to show that the Frenet-Serret frames are the same, and the Frenet-Serret and the curve, they pass through the same point. Okay, so you want to show that gamma 3 is gamma 2. Okay, and that means it is enough to show that the Frenet-Serret frames are the same. And remember, if the Frenet-Serret frames are the same, that will give you the curves are the same, because that is the argument that I gave here just now. All right, we have to just integrate the first member, which is the tangent vector. There is this initial condition that both the curves are passing through the same point, and the Frenet-Serret frames at that point are coinciding. We are using that. That is being used. That is being used. Okay, I'm not. Of course, it's not correct to say that if just the Frenet-Serret frames are the same, then the curves are the same. If you want to say that, that isn't correct. Okay, in principle, they could differ by a translation, but if they pass through the same point for a given parameter value, okay, then they have to be the same. Okay, so that initial condition has already been fixed. I mean, that is the reason why this g1 circle tv naught, that particular rigid motion was used. Okay, so so you see here, I have to just show that these two are equal. But you see, what does this mean? This means I have to show that t cap gamma 3 minus t cap gamma 2, okay, is equal to 0. So b cap gamma 3 minus b cap gamma 2. So I have to show this. Okay, but mind you, these are all vectors. Therefore, to show these vectors are 0, it's enough to show the norms are 0. And then the idea is that from the norm you can go to the dot product by taking the norm squared. So therefore, it is enough to show, is equivalent to showing the following, namely norm of t cap gamma 3 minus t cap gamma 2. So plus, say I want to show every norm is 0. But norm squared is convenient because norm squared is the dot product of a vector with itself. So, and the sum of squares is 0 if and only if each is 0. So it's equivalent to showing that sum of the squares of these things is 0. So n cap gamma 3 minus n cap gamma 2 squared plus b cap gamma 3 minus b cap gamma 2 squared this is 0. This is enough to show this. Okay, but you see, to show that this is 0, you use calculus and say that it is enough to show that the derivative with respect to s, mind you, these are all functions of s, it's enough to show d by ds of that is 0. Okay, then it means that this will be a constant. Okay, but the initial condition will tell you that constant is 0. because the Frenet-Serret frames are the same at S naught. Okay, therefore it is enough to show enough to show d by ds of this quantity here is 0, this whole quantity here. Okay, but you see what is d by ds of that, just compute d since at S naught the value is 0 because of the initial conditions. Okay, but what is d by ds of that? Norm squared is norm v squared is v dot v. So you use that. So what you will get is, you will get t gamma 3 cap minus t gamma 2 cap dot t gamma 3. So let me write something here. D by ds of norm v squared is d by ds of v dot v. Okay, and that is 2v dot v dot. Okay, by definition. Okay, and don't confuse the dot in between the v and v dot, that's the dot product, and the dot on top of the v is d by ds. Don't get confused. Okay, so therefore let me directly write it. So let me remove this d by ds, and what I have to do is just, there is a 2 here which will come out common. Okay, I will get v dot its derivative, so I will get dot minus t cap gamma 2 dot. Okay, plus then I will get 2 more terms similarly for n cap gamma 3 minus n cap gamma 2 dot, again n cap dot gamma 3 minus n cap dot gamma 2. Okay, plus b cap gamma 3 minus b cap gamma 2 dot b gamma 3 cap dot minus b gamma 2 cap dot. I have to show this is equal to 0. Okay, but I claim this is directly because of Frenet-Serret equations, because you see, watch this. If let's look at the first term. Okay, see this t cap and t cap dot, the dot product will be 0. That's because whenever you take a unit vector and differentiate it, the derivative is perpendicular to the unit vector, and mind you, t cap is a unit vector. Okay, therefore what happens is, in the first term, this t cap gamma 3 dot t cap gamma 3 dot, that is going to be 0. Similarly, t cap gamma 2 dot t cap gamma 2 dot will also be 0. So only the mixed terms will survive. So what you will get is, the first term will be, I will get minus t cap gamma 2 dot t cap dot gamma 3 minus so I will get this minus t cap gamma 3 dot t cap dot gamma 2. That is the first term. All right, and so it's just a matter of writing this down. And in the next step, what I'm going to do is, I'm going to just replace t cap, t cap, b cap, n cap. They are expressible in terms of t, n, and b because of the Frenet-Serret relations. So you just substitute that, and everything cancels out. You get 0 directly. Okay, you don't need to use uniqueness of the theory, uniqueness from the theory of differential equations. So the Frenet-Serret equations already have that power to show you that the Frenet-Serret frames are the same. Okay, you don't have to go to differential equations. Okay, so that's what I want to say. So you see, this is the first term. What is the second term? The second term will be, so this term is going to be, I will get similarly minus n cap gamma 3 dot n cap dot gamma 2 minus n cap gamma 2 dot n cap dot gamma 3, and plus the third one will be again and of course the factor 2 I forget, so I will get again a minus, so I will get a minus b cap gamma 3 dot b cap dot gamma 2 minus b cap gamma 2 dot b cap dot gamma 3. So you have to show this is equal to 0. So I'll just say let me say LHS. LHS is this, okay, but now you use the Frenet-Serret differential equations. So you see what is the n cap dot gamma 2 is actually, it is minus k of gamma, so it's minus k gamma 2, it's minus k gamma 2 t cap dot t cap, just t cap gamma 2, okay, plus tau gamma 2 times b cap gamma 2. Okay, this is the second Frenet. So this I substitute it here, all right, and similarly I have to substitute here. So this has to be substituted here, and here I will get n cap dot gamma 3 is equal to minus k gamma 3 t cap gamma 3 plus tau gamma 3 b cap gamma 3. Okay, and if you substitute it, okay, the second term will become 4 terms, and it will cancel with the other 2. You can see that immediately. This t cap dot, you can so this is by definition, k gamma 3 times t cap gamma 3, I mean n cap gamma 3, this should be, okay. This is the first Frenet-Serret, and this guy here is going to be k gamma 2 n cap gamma 2, okay. I mean, convert all the dots into terms without dots by using the Frenet-Serret relations, and then everything will get cancelled. Okay, so similarly, this guy here needs to be written as minus tau gamma 2 times n cap n cap gamma 2, okay, and this guy will become minus tau gamma 3 n cap gamma 3. Okay, you substitute all this and you will get 0. That's all. Okay, so basically, you see, you don't have to use the uniqueness of the solution of differential equations. The Frenet-Serret frame itself gives you that the Frenet-Serret differential equations itself, they give you this. Therefore, the Frenet-Serret frames are equal, and once the Frenet-Serret frames are equal, you integrate the first member, which is the tangent vector, and you get the curve, and of course there is already an initial condition. Okay, so everything is done. So I want you to understand that the Frenet-Serret differential equation is already giving you the equality of the Frenet-Serret frames. Okay, so that's what you have to appreciate. All right. No, that is how gamma 3 is defined, right? Gamma 3 is defined as G1 circle TV0 circle gamma 1. No. The point is that once you prove that this is equal to 0, okay. So your question is, where have we used this special rigid motion, right? See, once you prove this is equal to 0, you are only showing that the derivative of this is 0, and that will mean that that this is constant. See, it will mean that this left side is constant, but I want to show that that constant is 0. For that, I need that the Frenet-Serret frames are at least at one point they are the same, and that is exact, and for that I need that these two curves pass through the same point. Now, but that's exactly what this G1 circle TV0 does. TV0 makes sure that they pass through the same point, and then after applying G1, it also makes sure that G1 circle TV0 circle gamma 1 and gamma 2 have the same Frenet-Serret frame at that point. So that is the reason why this constant is 0, and therefore it is always 0. Yeah, of course, it is important that you are still working under the assumptions that the two curves that you started with, they have the same curvature and the same torsion. So in fact, this k gamma 2 is the same as k gamma 3, tau gamma 2 is the same as tau gamma 3. That is important. So that is also there in the background. That is being used. Okay, all that is being used. Okay, so is this clear? So I want you to appreciate the power of the Frenet-Serret differential equation. Okay, to get the equality of the Frenet-Serret frames. Okay, all right. So this is one part of the story. Okay, this gives the injectivity of the map. You take two curves, if they have the same curvature and torsion, then they are rigid motion equivalent. That's what we have proved. Now we need surjectivity of the map. That is, you start with two arbitrary functions. One is a curvature function, positive curvature function, which is C1, and you start with a continuous function, which is a torsion, which is not necessarily signed. Okay, it can be positive or negative or zero. You have to find a curve for which these two functions are respectively the curvature and the torsion. So this is the surjectivity part. Basically, the statement is that you are trying to say rigid motion equivalence classes of unit speed parameterized curves, they are in one-to-one correspondence with the curvature, with pairs of curvature and pairs consisting of curvature functions and torsion functions. That's what you are trying to prove. And what we have proved is the injectivity. Right? We have to prove the surjectivity. That means you give me arbitrarily, you give me a C1 function, which is a positive function, and another C0 function, which C0 means just continuous. Okay, C1 means continuously differentiable. And so you give me a pair. You give me a C1 function and a C0 function. Then you have to find a curve which is unit speed parameterized, for which the first function is the curvature function, the second function is the torsion function. You have to find such a curve. So that is what we have to do. Okay, and here you will have to use the existence theorem for solutions of differential equations, because basically what the strategy is that once you are given the functions which are supposed to be the curvature and torsion functions, if such a curve exists, then its Frenet-Serret frame has to satisfy the corresponding Frenet-Serret differential equation, which is completely determined by the curvature and torsion functions, which are already given to you. Therefore, first using the so-called curvature and torsion functions given to you, you look at the Frenet-Serret differential equation and get a Frenet-Serret frame first. Once you get a Frenet-Serret frame, from that to get the curve is not a big deal, because you just integrate the tangent, the first vector, the tangent vector, that will give you the curve. That is the strategy. Okay, but there are a few hitches. So I'll explain that. So we start. So for the surjectivity, we start with the following. Okay, for the surjectivity, we start with the following. So you are looking at a, there is a capital phi and there is a capital psi. Okay, and mind you, this is phi of s, psi of s. You are starting with a pair. Where is this? This phi of s is a positive function C1, so it is C1 on AB, and it is R plus. Okay, that means it's a positive first continuously differentiable function. That is what this phi of s is. That should be the curvature function. And the second function is going to be the torsion, which is just continuous and just real valued, it's unsigned. So the second one is this. Okay, so I start with the capital phi and a capital psi. Okay, we need to show that there exists a gamma of s in AB with unit speed parameterization by increasing arc length s, okay, such that the curvature of this gamma is exactly your capital phi of s, and the torsion of this gamma is exactly given by psi of s. This is what you have to show. This is the surjectivity. All right. So you have to construct this curve. So you see, if such a curve exists, then its Frenet-Serret frame has to satisfy the Frenet-Serret differential equation, and the Frenet-Serret differential equation is controlled by the curvature and torsion, and those are the functions that are already given to you. So therefore, first solve that differential equation. So we first try to solve the Frenet-Serret differential equation. And what is that? So you see T cap gamma, N cap gamma with the dot, and B cap gamma dot is equal to, here I have to write the, so here at this point I am supposed to put the curvature of gamma of s. So here I will put phi of s, okay. And so let me just write it like this. Let me first write it as it is. So k gamma of s 0 0 minus k gamma s 0 tau gamma s, then 0 minus tau gamma s 0, and then here I will get t cap gamma, b cap gamma, n cap gamma. So you have to solve this, okay. But the point is that see, when you write this differential equation, you're already assuming that there is a gamma for which there is this Frenet-Serret frame, and this differential equation holds. That okay. But what we are now doing is, see, to be very, very careful, okay. We are only solving a differential equation. The only thing that is that this k gamma is given to you, tau gamma is given to you. So basically what I'll do is I'll rub this out, okay, and I will replace them by what is given, okay. So let me get rid of this. So oops. So I'll replace k by the so-called k by capital phi of s, and so there's a phi s here, and then here tau should be replaced by psi of s, so there's a minus psi of s here, okay. And I am finding a solution to this differential equation. Now the first hitch is that, you see, when I solve this differential equation, I'll only get 3 vector functions. See, when you solve this differential equation, the theory of ODE will tell you that you will get a solution, all right. And if you want a particular solution, you have to give an initial condition. So you will get only 3 vector functions. It is not even clear that those 3 vector functions are actually the Frenet-Serret frame for a curve. That is the critical thing, okay. I will only get a solution to the differential equation. So what I should do is, you see, I rub out all this, I'll rub out all this and simply write it as, I have to solve the differential equation, and I will get for, some fs, okay, gs, hs, and then here it will be f dot s, g dot s, and h dot s. You have to only solve this. You have to first solve this differential equation, okay. Then you have a job to do. You have to, of course, if you want a particular solution, basically you are trying to find a particular curve. You want at least one curve. That means you want a particular solution of differential equation, so you have to give some initial condition, okay. And the initial condition is that you have to fix a Frenet-Serret frame at some point. Basically you have to say the curve is going to pass through some point, and you are going to say at that point this is the there is one Frenet-Serret frame that is given to me. That is the initial condition I'll have to put. So you see, I solve this differential equation. The solution of this differential equation is going to be there. I'm going to get 3 vector functions f, g, and h, all right. And I can even put this initial condition that f, g, and h at one point, let us say parameter value s equal to s naught, they are equal to a given orthonormal frame, which I can take as, if you want, I can take I cap, j cap, k cap, which is the, good old unit vectors along the 3 directions. So I can fix a point s naught in AB, okay, a parameter value, and I can specify at that point the Frenet-Serret frame is the standard I cap, j cap, k cap, okay. Even if I do that, what will happen? I will get this f, g, and h. I will get 3 vector functions, which at only that point, okay, I get that Frenet-Serret frame ijk. If I change the point, there is no guarantee that they are orthonormal. That's what I want you to understand, okay. But the magic is that they will always be orthonormal, okay, and that is because of the skew symmetry of this matrix, okay. So that is the amazing thing. So that is again, the power of the Frenet-Serret matrix being skew symmetric, okay. So let me say the following thing. So you see, again, let me repeat, okay. You solve this so-called Frenet-Serret differential equation, you will get only 3 vector functions, okay. You can even, if you put an initial condition, so you can put an initial condition that these 3 vector functions at a given point are 3 known, they correspond to a fixed orthonormal frame. But that doesn't directly seem to tell you that at other points also these three functions are orthonormal. See, orthonormality is two conditions. One condition is that they have to be mutually orthogonal, all dot products must be 0. That is orthogonality. Normality is a condition they are all unit length. That means the self dot product should be 1. Okay, just because this happens at one point for the functions f, g and h, there is no guarantee it will happen at other points. But the beautiful thing is, because of the skew symmetry of the Frenet-Serret matrix, okay, it will happen everywhere. That's what I want you to notice. So that is just so the here the linear algebra is working. All right. So so we will see that. So I'm just trying to stress the point that one would usually miss. See, one could just say that I mean, one could do the following mistake. As I first wrote it out, if I assume that there is a gamma like that, okay, with these curvature and torsion functions, then I can carelessly write f, g and h as just t cap, n cap and b cap of gamma. And since I have written t cap, n cap, b cap of gamma is equal to matrix times t and b, and I know solution of the solution of that ODE exists, then I would have assumed that therefore I have got t cap, n cap, b cap. So integrate t cap and you should get gamma. But that is wrong. Where is it wrong? Because you see, I have already assumed that there is a gamma for which this f, g and h are exactly the t cap, n cap and b cap. That I should not. That's where you have to be careful. What the theory of existence says is that there are three functions f, g and h, vector valued functions, which solve this ODE. Okay, and the only initial condition you can put is at one point they give rise to an orthonormal frame. There is nothing to suggest that at other points also they will remain an orthonormal frame. Once you establish that it is an orthonormal frame everywhere, then you can fit a curve to that by simply integrating the tangent vector. And then you can prove that for that curve, the curvature function is what you want, what you specified it to be, and the torsion function is what you specified it to be. Okay. So the big deal is that at one point, this solution being orthonormal forces the solution to be orthonormal everywhere. That is the critical thing. Okay, that is the power of the skew symmetry of the Frenet-Serret matrix. Okay, that's what I want you to notice. So let me say that by the theory of existence of solutions to first order simultaneous linear ODE with existence with uniqueness of a solution for a given initial condition. Okay, there exists Fs, Gs and Hs S in AB such that they they satisfy the above ODE, and such that at S is equal to S naught, you see Fs naught, Gs naught, Hs naught is simply I cap, J cap, K cap. Okay, so this is the initial condition. Okay, so I will just put a caution here. The caution is it is not immediately clear that Fs, Gs, Hs is always an orthonormal frame for every S. So I will put this caution. Dangerous bend symbol. Okay, it is not clear that Fs, Gs, Hs form a right-handed orthonormal frame at each S belonging to AB. Okay, just because they do so for S is equal to S naught. So this is the whole point. Okay, and here is where the skew symmetry will tell you that it will always happen. Okay, and the point is, once you have that, integrating the first function, which is the tangent vector, will give you the curve. And then for that curve, you can, once you find the curve, then the usual Frenet-Serret relations are satisfied, and that curve will have the specified functions as the curvature and the torsion functions, and you're done. Okay, so that's what we have to do. Okay, so I will continue in the next lecture.